Today's lecture is going to be about optimization. Before I start, and we'll talk about what that means in the context of this course today. Guys, quiet down a little bit, please. Thank you. All right, so the outline of the overall lecture today is going to be, we're first going to give a kind of into optimization, really more as an introduction rather than a technical introduction. But actually, one of the key points of optimization, in AI at least, is just thinking about problems as optimization problems. We'll talk about what that means, and then we'll talk about a little bit more in terms of the distinctions of different types of optimization problems, and we'll talk some about convexity. So we'll spend a good amount of the course talking about convex optimization, because it does have a lot of importance sort of as these categories of optimization go. And finally, we'll get to how we actually go about solving these problems in optimization and what that means to solve and the techniques you can use, both kind of off-the-shelf techniques as well as kind of what's happening behind the scenes. So first, some quick logistics. So the homework 0 was due last Friday. I think there was a little bit of misinterpretation of the no late days policy. So we said you cannot use late days for homework 2, for homework 0. Some people interpreted that to mean if you turn in it late, you will just get the 20% off per day, up to 2 days. Our intention was that after the deadline, that was a hard deadline. But I think enough people misinterpreted it that we will actually allow you, if you have submitted after Friday, you will just get 20% off. The page is quite clear that there was no homework late days allowed for homework 0, but whether or not that meant that you get 20% off per late day or just no credit was ambiguous, so we will allow 20% off up until Sunday. So 20% off Saturday night, 40% off to Sunday night, and then after Sunday, there's no credit. So just to be very, we didn't intend this to be ambiguous, but maybe it came across as such. In all future assignments, you will have 5 late days. That means over the 4 assignments, you have 5 late days. You can use at most 2 of them per assignment, though, right? So after 2 days, you'll receive 0 points on your homework. Even if it's just a few minutes late, we have to have a cut. It will get no credit for your homework. So please don't try to wait until an hour before deadline to realize you have a problem with AutoLab. Submit solutions early, or there will be problems. And then if you use your 5 late days and you take additional late days now, so you've used like all your 5 late days in the first 3 homeworks, and on homework 4 you submit 2 days late, that will then be 20% off per day. But again, after the 2 days, you get no credit. Does that make sense to everyone? There's no ambiguity there? Okay. It wasn't meant to be complicated, but somehow I think that things came across as complicated. There's also a little bit of inconsistency on the website, I think, that we just want to reiterate what I said in class, which is that all homework, both programming and the written portions, have to be done independently. So you can talk about it with people, certainly, but when you stop to write up your problems, you have to put any notes you had from those discussions away and do it all, the written portion and the programming portion, yourself. Okay? And the other good news, which I guess is sort of, it's good news, really, but it turns out that actually, as we expected, everyone that submitted a homework 0 so the threat of only the top credit people getting let in, as we sort of predicted, is not the case. It turns out that there actually is space in the course for everyone that submitted an assignment. You will, in fact, get, and you didn't have any issues with it, you will, in fact, get off the wait list. So you should have all gotten an email to that effect. If you haven't, let us know, but you should have gotten that email. Okay, any questions so far? Okay, so let's just jump right into the actual content of the lecture. All right, I really enjoy this topic a lot because optimization is something that personally, a lot of my research, I think is one of the most fascinating topics in AI right now. And the interest, I think, stems from this really sort of interesting property we have. So far in class, we've been focusing on kind of discrete problems, right? In search, you had one of some number of discrete actions you could take, and you have to plan out a sequence of actions to reach the goal, essentially, right? But we're still talking about kind of in this discrete space. Now, the interesting thing about this is that when we move to optimization, and what I'm referring to here is optimization, though that term actually is very loaded. So I'm referring here to continuous optimization. In other words, optimizing over continuous variables, but I'll define it much more in a second. Something kind of impressive happens. So in most discrete search problems, the search space, the variable space is discrete, as you would expect. And that means the number of possible solutions you could have to a problem is finite, right? It's some fixed amount. It could be very big, but it's still finite. Yet at the same time, the running time of these things is often exponential, in the worst case at least. So we didn't get into this, but the running time of A star, even the algorithms, are always exponential in the worst case, right? You can always have essentially a situation where you have to explore, expand a lot of nodes, all the nodes, or almost all the nodes, given your, depending on your heuristic. And so solution complexity is exponential. Now, we can contrast this with optimization. And for this, at least, I'll be talking about a subset of optimization called convolution, which we'll talk about a lot in this class. But here you have a different situation here. So here, the variables you are making decisions about are all continuous. So they're real valued variables. That means, by definition, there's going to be an infinite number of possibilities. Yet, for a lot of practical problems, you end up having polynomial time algorithm systems. So it's a very sort of interesting, more solutions, but somehow the problem actually becomes due to this, which is not actually uncommon in computer science. You see this a lot, but this is a very nice property of these optimization problems. What's the question up there?
Are these solutions approximate?
No, they're exact solutions. Exact solutions in polynomial time. At least to numerical precision. I mean, to numerical precision yeah. I have that right here. Oh, in my pocket? Belt, okay. All right, sure. And in fact, I think one of the most significant in AI in the past, say, 15 years, though it might be, thanks, though it might be more than that now, actually, as a solution technique. These techniques actually were not developed in AI. They were much more the domain of things like operations research or signal processing. But if you open a paper now in an AI conference, chances are just as much as you'll find an optimization problem, formulation of some problem, than a search problem, right? So it's become really an integral part of AI and kind of the continuous counterpart, in some sense, to search in a lot of ways. So I'm just going to go through a few definitions right now. This is how I'm going to write optimization problems. And I'm going to actually dwell on this a little while because the notation here is pretty important. So I'm going to write it as minimize, below that, some function f of x subject to x being in some set C, right? And here, there are, so let's highlight here. So this is an action. That means what we're doing with the optimization problem is minimizing it. This is not the same as min is actually the minimum value of the problem. And argmin we'll talk about later. But minimize is the actual operation we're applying here. So that's sort of so I'll be kind of pedantic about saying minimize, the whole word loaded in math notation. But what this means is we want to find a value of x that achieves the smallest possible value of f of x over all points in C, the set C. Okay? And just some quick kind of definitions here. We call x, the variable x, the optimization variable. And for the most part, I'm going to consider x being a vector in Rn. That means it's an n-dimensional vector. And I'll write that as, I'll say I'll just put a few little notes here. But I'm going to write x in Rn. X is a vector in an n-dimensional space, real valued elements. F, which is a function mapping Rn to R. This is the optimization objective. That's the thing we're trying to minimize. It's important that it is real valued, the output. Otherwise, it looks like it has two components, right? Some subset of Rn then is called the constraint set. Points in the constraint set are called feasible points. Points outside the constraint set are called infeasible points. And just to sort of, again, be clear, x star, which will also call the argmin over x and c of f of x. Optimal solution, right? That's the actual argument that minimizes that expression. And f star, or equivalently f of star, that's equal to the min over x. So just a little bit of information there. I'll use this in the future to distinguish between these two. If you want to really be pedantic, you can call this an inf, an infimum, not a minimum, not a min there, but pedantic. Yeah.
Check. Is the meaning of the augment x and c notation and the minimize x notation, or is that just the informal version?
So min here means the actual value. This is a real. Okay, argmin is the actual argument that minimizes it. So argmin is the solution. Okay, so when I say argmin, I mean actually the optimal x that minimizes that. Min means the lowest value, and minimize means the overall operation of solving this problem, right? And I will distinguish between those three things. So if it's confusing, do ask me about that now. Okay, so why should you kind of care about this? I'll give a few examples. This is an example I give for the first example often because I really like it actually. So it's one of the simplest problems you can imagine. So say I have a bunch of cities, which are points on a 2D plane. We'll even assume, don't even assume they're on a globe. Just points on a 2D plane that minimizes the sum of distances to all those points. So what is that location? Does anyone actually take a guess? If you know this already, don't answer because there's just an answer you can give. But does anyone have a guess about what that point is? It doesn't know the answer. So the centroid, right? So people, I think the thing people actually, sorry, what's your name? Ashwin. What do you mean by the centroid?
So like the average of all the x coordinates and the y coordinates.
Yeah, exactly. So I would think that too. So I would think you take all those points and take the average of them, right? That makes perfect sense. That seems like the point that should minimize this, right? I'll try to convince you why you're wrong, though. So think about 3 points, right? 2 that are like right on top of each other, and 1 that's over here. So those are 2 points, and that's 1 point there. The point that minimizes the sum of points here. All right. So the center would be somewhere like this, right? Moving. I decrease my distance by a unit of 2 and only increase it by 1. So I have a shorter. In fact, it's this point right here is the solution. That would be the point that minimizes the distance. And if you have, in general, if you have points in a line, what point is it that minimizes their distances? The sum of distances. Right? It's the median, not the mean. Right? So the average is the mean. In general, on a line, it's the median. So in 2D space, though, what's the median in 2D space? I remember I got this problem in my high school. We had like problems of the month in my math class. This is one of the problems of the month we got, and I remember it just infuriated me because I kept trying to like come up with some concise description of what this point should be, and I couldn't find it. Actually, you can in 2D. You know that you can. I didn't figure it out back then, but you can do it in 2D. But in higher dimensions, there actually is no sort of natural, compact description about how to find this. The way you find it, in fact, is, for lack of a better term, is just by solving an optimization problem. So this seems like kind of a cheap solution here, because I'm not actually telling you how to find this. But I will, by the end, kind of tell you how to find these things by the end of the lecture. So the way you think about these things, oftentimes, is not by trying to sort of give a procedure for finding this point. It's about writing this problem as one that solves an optimization problem. So in this case, I have a bunch of points, and actually I can be more specific about what kind of dimensions are those points. I have a bunch of points y, y1 or ym, and what I want, the way I can find this point, it's called the Weber point, the geometric median sometimes it's called, is I'm just going to write the solution here of the optimization problem of minimizing over x of the sum of distances between x and y. Okay. So this is how you sort of, in some sense, solve the problem. And we'll talk soon. I'll code the last slide actually how you would actually implement this, but with a very high-level language, maybe still isn't. I'm not that satisfied. But there is really no way, in some sense, to really solve this except writing it as kind of optimization problem. Here's another example I really like. So here is a picture. This is taken from a paper from a few years ago. Here's a picture on the left, and here in the middle is a corrupted version of that picture. So what they did was they blurred that picture with the Gaussian blur. You know what that is. They blurred that picture, and then set half of the pixels in the image randomly to be either 0 or 1. So that's called salt and pepper noise. So they blurred it and kind of added this noise there. And if you look at that image, there's, doesn't seem to be that much there. It seems really kind of confusing and noisy what that image actually is in the middle there. And after this then, you run a procedure, optimization-based procedure, to try to recover the underlying image, just given that middle one as input. And what this procedure returns is the image on the right here. So that's sort of amazing, actually, right? I mean, there's details here that I would never be able to even see in that middle image, but by doing this optimization procedure, you can actually find and recover the image on the right here. And so what they're doing in this case, actually, the way they do this, for those that care, we'll get into a little bit more of this kind of stuff later in the course. What they do is they minimize over some new image x. So x is a new image. But they try to minimize the error between x also blurred with a Gaussian filter. So k is a Gaussian blur convolution. Again, if you don't know about this, don't worry. It's just an operation that kind of blurs the image. And so you find an image that when you blur it, looks like the target, but in the absolute value sense, which actually allows you to have some noise to account for this salt and pepper noise. Plus some term here that actually is called a pool variation regularization term. And so that term is a little confusing here. What it does is that term penalizes differences between successive pixels, between one pixel and the bottom one, the one to its bottom, and the one to its right. And so this is sort of a smoothness that's placed upon the images, that when you use this in this way, actually recovers very realistic and nice images. Again, just given that middle one. Yeah?
I just have to ask, is the Gaussian blurring stochastic or not?
So the question was, is the Gaussian blurring stochastic?
Yeah.
No, it's deterministic. I mean, it would be very hard if it was stochastic.
Yeah.
Yeah. Sorry, what was your name?
Matthew?
Matthew.
And on the previous slide, I already moved past it, but was that supposed to be an L1 norm rather than an L2 norm in the previous slide? You had 2.
No, that's an L2 norm.
Okay. Then is this the sum
importantly, it's the L2 norm not squared. It's the L2 norm. So, again, some more definitions here. So when I say this is an L2 norm. And what I mean here is the square root of the sum of all entries inside the square. Okay. If I didn't have that square root there, that would be an L2 squared norm, and that would actually just be the mean that would give that. This one, though, is this right. And we'll try to keep my definitions over here, so. And if I had this thing squared, then there's no square root, right? So this. Okay, and finally, I'll give an example from robotics. Path planning already a fair amount, and we talked about search. But it turns out that oftentimes in robotics, something like the shortest path plan is not necessarily what you want when you're making a plan for a robot, right? You actually want something like the lowest energy plan or something like that, the lowest actuation cost plan. And you maybe want to hit obstacles, but you also slightly prefer kind of being far away from them or things like this. There's a lot of things you can add to a robotic path planning problem that actually makes it a little bit harder to solve than just a simple kind of shortest distance path problem. And so a very common trend in the past few years in robotics has been to frame path planning problems and manipulation problems as optimization problems.
One common way of doing this actually is to say that what I want to do is I want to minimize my sequence of actions. I'm going to call my actions U here. Such that, subject to the fact that my states, which are denoted as xt, have to evolve according to some dynamics function of the robot. This may actually include not just the robot's position, but also its velocities, its masses, things like that. Subject to constraints, if x is in free space, you can't collide with obstacles. If you have other penalties though, like I want to benefit more being further away from obstacles and stuff like this, and the fact that you have some initial state, a goal state, and both initial state and goal state. And this seems very hard. And I have to say, unlike the last couple problems, this one is non-convex, so it's not necessarily one you can solve very easily. But nonetheless, this actually has become kind of a standard way that people actually solve robot manipulation tasks, because the paths that are given by these sort of more discrete search-based techniques often just gave paths that were just too jerky to really be of use to the robot, whereas these kind of paths are much smoother and can kind of produce much more realistic and natural type actions. So this is how a lot of planning kind of actually functions in practice, though with the big caveat that these problems can be very hard to solve, and unlike something like ASAR, when you can't solve them, it oftentimes is very hard to know, how to manipulate your problem in a way that you can solve it. And the last one we'll talk about too is machine learning. So we're going to cover, this question.
I had a question 2 slides before. Sorry.
Okay.
In that, is K the blur kernel would K be the blur kernel or?
Yes, K is the blur kernel. Again, the details here are not important, so if you didn't fall into that, don't worry. It's just an example that I think is very visually impressive. Okay, so lastly, machine learning. So machine learning actually is all about optimization. Virtually, and we'll talk about this much more when we talk about machine learning, but virtually every machine learning algorithm is of the form minimize over some parameters data the sum of losses between my prediction and the actual output. I should clarify, this is the most supervised learning algorithms are of this form. Where here y is an output, it's a label you're trying to match, and h theta of x is what's called a hypothesis function that makes a prediction of its output given the input there. And that function is parameterized by the parameters theta, and the goal of machine learning is to find some parameters that minimize these losses. That was very fast for machine learning there, for all of machine learning, but we'll come back to it at least for a few more lectures later on in class. So I'll just skip over this entirely, but the short of this is, if you care and really like machine learning, you should probably care about optimization. Alright, so to sum all this up, I think one thing that's driven the adoption of optimization as this sort of primary force in AI, or one of the primary forces in AI, is this very nice notion of kind of a separation between the formulation of a problem and the way you solve it. Okay? So I, so far, on those past pages, just formulated some problems, right? I told you what the problem was. I did not yet tell you how we actually go about solving it. Right? So I didn't actually say, and we solve it by this procedure. So in some sense, I haven't actually told you anything, right? But I haven't actually told you how you solve those problems. I've just written them down. But what's very nice about optimization is there is a certain category, a certain way of delineating problems that lets you specify them in certain standard forms, such that once you've written it in that form, it essentially already is solved. So there are off-the-shelf software packages you can use that once you write a problem in a certain way, it can be solved. And even if you don't have that, right, even if actually your problem is very hard to solve after you've written it down, you still have a very nice way of evaluating how good your solution is. And it's going to say, how close my solution actually comes to really solving the problem or not. Right, so there's this very nice separation between the problem I want to solve and how I'm formulating that, and the way I actually go about solving it. I think that's actually one of the cruxes of optimization and why it's a powerful tool in a lot of AI. Any questions before I move on? Okay, so let's talk a little bit about different types of optimization problems here. And If you sort of dabble in the space a little bit, you may come away very confused, and I think rightfully so, because there's this wide plethora of names people use to describe every kind of problem, and they get very convoluted after a while. So there are things like linear programming, which we're going to talk about next lecture, quadratic programming, nonlinear programming, that's what it really means, semi-definite programming, integer programming, geometric programming, and then all the combinations, like mixed linear binary integer programming. I thought it'd be mixed integer binary linear programming there. And swap even some of the names here. But a lot of these things get very kind of convoluted, what people call them. And it's very hard to kind of categorize and delineate all the different types of problems people have here. And so you will eventually start to the point where you can easily pick out what people are meaning when they say these things. But for the first bit at least, we're not going to go into too much detail there. We're going to focus on a few kind of key distinctions between different types of optimization problems people actually care about. So, the two big dimensions that we're going to focus on, really through a lot of this class, and techniques about how you solve these things, are the difference between convex and non-convex problems. We'll talk about that a lot today, actually, about what that means. And then constrained versus unconstrained problems. So problems that have a constraint set of where X can live, and problems that don't have that constraint set. And in fact, if you look at what we cover in this course, actually a lot of it fits nice into one kind of buckets here. So most machine learning problems actually take the form of convex and unconstrained problems. This is sort of all not all machine learning, but the majority of machine learning that happened like in the 90s and 2000s until deep learning came back and was popular again. Then deep learning, in fact, the big difference there is actually non-convex. Now it's still unconstrained division, but it's non-convex. Unlike a lot of machine learning before that, which was convex. But we'll give a whole history of deep learning in a later lecture. Then you have a whole class of constrained problems, and when they are convex, well, not entirely, but one big class of problems that are convex but constrained are linear programs, we'll talk about next time. And then on kind of the hardest side here, which are constrained non-convex problems, we'll talk to about integer programs, which kind of fit that mold down, being both non-convex and having constraints that are hard to satisfy. So this is not by any means an exhaustive list. It's just showing a few different types that rely on each of these axes here. But the big point I want to make is sort of much more about these different types of problems rather than about the individual designations you may see in other kinds of names like linear programming, quadratic programming, etc. Any questions? Alright, so let's first mention briefly the unconstrained versus constrained case. So constrained optimization, or unconstrained optimization is kind of the obvious one. You just have some function, and I want to minimize over x at f of x. Right? That's the unconstrained optimization. And it's very nice because in that setting, every point you may have is actually a feasible point, right? Every point attains legitimately some objective f of x. And so your sole focus is going to be on finding an x that minimizes f of x. In the constrained case, however, you have to kind of satisfy both these two things. You define an x that minimizes f, but also is in your constraint set. In fact, find the smallest one, the one that gets the smallest value of x out of all the points in your constraint set. That kind of looks like this. And the view I'm showing here is a top-down view of a function. Those little circles there, they don't level sets of the function. They're coming out at you from the board. And so the minimum of that function would be right there, in this case. Whereas in the constraint set, noted there by that polygon there, that would then, the minimum function value of the function, minimum point of that function, would actually be on that corner there. You can't actually get to the minimum anymore, it's not constrained, so the optimal solution now is on the board with that function. Yeah? Yeah, so the no. if I just shifted that over a little bit, right, and I had like a polygon that was around this thing, then it's still in the center, but not on the boundary. However, I think you asked a great question because for certain classes of objective functions, and these are the ones that are paired by linear programs, we'll talk about a lot more next lecture, then yes, you actually do. You are guaranteed to have an objective, an optimal system that lies over the edges. But in general, no. In general, because, I mean, you could just shift that thing over, right, to have it be around it. Okay. So. And in general, it can be hard to sort of, it's always easy in 2 dimensions, you can visualize things, but in higher dimensions, it can be kind of hard. Because they can lie on some of the borders, but not other ones when it's central like that, so you can have ones that are on some edges but not on the corners. And in fact, a lot of this one's kind of also seems relatively easy, right? Because that set there is an equal set, say. But it turns out that for a lot of problems, even just finding a feasible point can actually be quite difficult, right? So you can make problems where just finding a point in C, even if C is a convex set, essentially it's as hard as solving the problem to begin with. So you can't really go about it the same way as you do on constraint optimization. And so because of this, it typically uses a very different method for solving these classes of problems, and we'll actually cover them in some detail as a strain case rather than the next big distinction that I want to bring up here is that of convex versus non-convex optimization. This is also a really important one. So historically, if you look at the history of the literature, people discovered optimization, I guess I'll simplify a little bit, but people first came about optimization in a lot of popularity through linear programming. Linear programming, which is the next time, is one that we know we actually can solve efficiently. Though in theory that actually was only proven relatively recently in the 80s. 70s. But it was long practical before then. And so people kind of differentiate between linear and non-linear programming. I mean, linear programming was easy, but non-linear programming was everything else that must be hard, right? And then people realized after kind of a while, and I think this sort of became very clear and well accepted in the 80s and 90s, this wasn't the right distinction. So the actual distinction between hard and easy problems is this notion of convexity. And so problems that are convex versus non-convex. Now I'll talk about why that is right now, but before I talk about why that is, I want to just write quickly sort of a vacuous statement here. But what a convex problem is an optimization problem just like this. Maybe I should write this down. I think every problem is of this sort. Our optimization problem is minimize for x, subject to x in C. And for this to be a convex problem, we need f to be what's called a convex function, and C to be what's called a convex set. So again, that's sort of a vacuous definition. But let me describe what I mean now by those two things. So a convex set, the first thing I'm going to here. Any questions yet? Still? Alright. Convex set is a set where if I take 2 points in the set, call them x and y, and I consider the line between these 2 points. Well, think about the line. And the way you write this line is you write it as theta of x plus, theta times x, 1 minus theta, plus 1 minus theta times theta. For theta being between 0 and 1. And for different values of theta, then this form here will sweep out the whole line between x and y. Okay? And a set is convex if, for all x and y in the set, every point along this line is also in the set. So that means that things like this, unless there are convex sets, they can have corners, they can have edges, they can be smooth or sharp or whatever. But every 2 points that I have in that set, that I draw a line between, that line, whole line, must also stay in that set. This contrasts with a set like this, on the right here, which is a non-convex set, because I can take 2 points, these 2 lower portions there, draw a line between that, and then you have a point which lies outside the set. So some simple examples of convex sets. One is just all of Rn would be a convex set, right? So if I take 2 points in Rn, I draw a line between them. That point's also an Rn. Convex set. So are intervals. So if I have a set like this, interval, I have 1, 2. And intervals essentially are kind of like rectangles in this space, right? They're saying that one coordinate is less than something that has to be greater than some bound and less than another bound, and they have a bound for each coordinate. Some of these could be empty, by the way, so this one could go off forever. It's still a convex set. Some of the bounds can be infinite, but all inequality sets like that are convex sets. Another one, which will become very important next class, are linear equalities. So if I have, and I'm not going to use too much linear algebra, I'll use a lot more linear algebra next time. A little bit of linear algebra this time, just vectors, so it's pretty simple. Now I'm having a matrix there. So if I have a matrix expression, AX equals B, that's a convex set. So if I take 2 points on that, right, I'll show this one. It's pretty easy, right? So if AX equals B and AY equals B, again, these don't have to be square matrices. They should actually probably be a wide matrix, right? So there are many solutions here. And if these 2 things both hold, then well, A theta X plus 1 minus theta Y. This also you just separate them out. You'll see that right? So that's the convex. And also mentioned here is the intersection of convex sets. I won't show that one. That's pretty easy to show also. One line and 2 lines of that there. So if I have a bunch of convex sets Ci, I think their intersection, that also is a convex set. Which could be empty, by the way. The empty set's a convex set, right? 2 points that are empty. You can't make more than X, or that is in a sense, it's that. But the intersection in general of convex is also. Alright, so a few more definitions, then we'll ask everyone a question. I'm sure you're actually waiting that. Yeah.
What about the infinite intersection?
So what was that?
Infinite intersection.
The question was an infinite intersection of convex sets. So yes, that's still a convex set. Yeah, it could be empty. Whether they're open or closed, I actually don't care about at all here. So they can be open or closed. That's sort of all okay. There's only points in the interior, right? You never go outside those 2 points. So we typically talk about closed sets in general because kind of open sets are strange to talk about, at least from a numerical standpoint. What that really means, but they have all those. What was it? I'll try to remember the past couple days. It's a great strategy, but I don't always do it. So remind me if I don't remember. Alright, so a couple more definitions here, and then we'll move on to asking useful questions. Alright, so a function is convex. Function now. So this is a convex set. Sets. And a function is convex if well, it has to be a function from Rn to R. It only applies to real value functions. That's about real value functions here. A function is convex if f of theta x plus 1 minus theta y. I should really have this in my slide here, but I should really write that down. Whenever I say theta here, I'm always talking about theta between 0 and 1. So I mean that here too, theta between 0 and 1. The function evaluated at a midway point between 2 points is less than the average of that function. At this point. And that's sort of a weird sort of parse of what that means, but it's actually really graphic. It's much easier to show that graphically. What that means is, if I have a function, and I take 2 points on that function, this over here refers to the line that connects those 2 points. Right? That's the line between them. And what convexity says is the actual function value lies either on or below that line at all times. So that's the definition. There are other better ways of characterizing convexity, which we won't go into because unfortunately we don't have too much time to go through this whole. There are whole multi-unit courses and multi-course sets on this topic, so we won't go into it too much. But this is what the definition of convexity is. Yeah. Yeah, so the function here, I consider 2 points in the function. The line that connects those 2 points, this one here, that's this right-hand side. And what convexity says is the actual function value, the value with midway points, has to lie below this line. Okay. Yeah.
If the inequality is
Yes. In fact, there is something that is one definition of strict convexity. Actually, is the name for that. But I'm actually not going to focus on strict convexity or strong. There's a whole different type of classes that use the same. Yes, that actually is strict convexity there. But it doesn't. Yeah. So there is, but we're not going to worry about that. We also said that if negative f is convex, then f is concave. Right? So, which is also equally kind of special. That means is always lies below. These things always lie below those 2 points. And importantly, there's plenty of functions that are neither convex nor concave, right? Because that function would neither be convex nor concave because there are points that lie both above and below a line between points. And if a function is both convex and concave, then it's actually what's called affine. And affine functions have to be of the form like this. They're a linear function plus a constant term in x. That's the only function that can be both convex and concave. And in fact, in that case, as you might imagine, that thing holds with equality, so it both holds with bigger than or less than or greater than or less. Greater than or greater than or equal to a. Yeah.
Is this definition extended to multivariate?
Yes, absolutely. So, what was your name? Max. So yes, that's actually very, very important. This is a multivariate definition. So here, x and y are both vectors in Rn. And the way to think about that is, think about it in 1D still, but what it really means is that you have 2 points on, a parabola or something like that, right? You have 2 points there, and the line will still lie above the interrelation of those 2 points. But theta is always a scalar here. Theta has always been 0 and 1. But x and y, very, very importantly, are vector valued functions. Because most functions of interest you want to optimize are, in fact, multivariate, or they're a little bit more. Right? They take vector input rather than they're scalar valued with vector input. Yeah.
So does it matter if you are trying to take argument of f of x, and f of x is not convex, then it might get certain open.
So I'll talk about that a lot in a second, about optimization and local optimal. So here are a few examples. I don't want to spend too much time on this, but I have a question about them next. So, you look at the exponential negative logarithm. That one's interesting because actually its domain is only positive x, strictly positive x. The squared Euclidean norm, plus the actual just Euclidean norm. Those are both convex functions. And one kind of important one is that the non-negative weighted sum of convex functions is also convex. So if you have a bunch of convex functions at Fi, and find some non-negative weighted sum, so the sum has to all be positive there, and that function is also convex. We won't prove those, but prove these are all very easy to prove, actually. Okay, so let's ask a few questions. So here's our poll. Which of the following functions is convex? Functions or sets are convex. So two convex sets, C1 and C2. Is their union convex? Yes. It's like pretty here and I'll go back to this. This is actually a multiple, it's like a check each one separately here. That only one is convex. You can check yes or no. Is there union convex? The set X and R2, I'm not going to actually involve this little guy here, but the set X and R2, the points are all positive, and the product x1 times x2 is equal to 1. The function x1 times x2, that's mapping from R2 to R. And the function x1 squared plus x2 squared plus x1 x2. Yeah.
Yeah, some people x is positive or 2 is negative.
Oh, sorry, this should be positive. Yeah. Trust this. Use this. Not my wrote here. My screen is too big. Yeah. Yeah. If you didn't see the x bigger than 0 here, then or something like that, then it's not here. Again, the bullets actually don't count for anything, so. Well, sorry, the fact that you do them counts very much. What you answer does not count. We want you to just think about it and answer what you want, but it's very important you check something before time expires, so we'll do 10 more seconds. Maybe longer than 10 seconds. Maybe a little bit. Yeah. Oh, talking about the shape of functions. Alright, we'll do maybe 20 more seconds. It's going down. Alright, so. Everyone voted? 37. Alright. Okay, so, good, yeah, so some pretty nice, I mean, the majority of the class is correct here, for all these. So, the first one is not convex, in fact, right? That one's hopefully pretty intuitive. If I have 2 points, like two sets like this, they're both convex. Their unions on a convex set, obviously, there's one in the middle there, they're not really set. The second one is convex, so it's not convex if you don't have a greater than 0 thing. The set is this set here, so the set of these points here. which is a convex set. Any 2 points in that set are in fact the line between them is in that set as well. This next one is not convex. This function f of 1 times x1 times this is not convex. I won't show why actually. It'll just get a little too much time if I show all of these things, but I won't show that. But you can pretty easily come up with an example of a 2 points. The way you show that, by the way, is just find 2 points where their average does not in fact lie below the curve. It's very easy to do that. Someone that you might even know about 2 points that they pull out their head. This last one is convex, which is kind of interesting, right? So it turns out that that one's a little tricky to show. It's actually not tricky at all if you have a little bit more advanced notation than what we use so far. But it turns out if you take that one, you can think of it actually as something a little bit like a quadratic form in both variables. So it's something like this. This is actually equal to x1 to x2 times, I believe, 1, 1, 0.5, 0.5, right? 1, x2. Which you could actually also write as this times the square root of this thing, all squared, and this is actually what's called a positive definite matrix, so that actually is the fact that don't worry, by the way, you shouldn't have to know any of that. Of course, it's just if you're curious about how you do it. This is just sort of to see what people's intuition was about these things. If you didn't get any of those, don't worry. I'll recommend to have your intuition by that. Yeah. Positive that. Yeah. Okay. So now you see a couple examples. This is just a few examples. Hopefully showing you that something else is the sort of space of all of these things is actually quite rich. This can be kind of rich functions you don't quite expect that do in fact still captured by this notion of x. So then what's the real significance of convex optimization? And the crux of it really is in this very simple term, which I think was actually alluded to before, and that is that in a convex optimization problem, all local optima are global optima. So if I have a solution that nearby me looks good, the best point of the points that are close to me, for a convex problem, that will actually imply that that point is globally optimal. The proof is very simple, so I think that should be worth going through. Before we do, we're going to have two definitions. So, first of all, a point x is called globally optimal if there's no, it's sort of the obvious thing, right? If there's no y, such that the objective value of y, is lower than that of x. Strictly lower than that of x. And a point is called locally optimal if there's some region around it, such that for any points in that region, they're less than that region away. And r can be as small as you want, but it has to be some sort of fixed r. Some small fixed r, for all points that within that radius of the point, there's no better point in that radius. And the sort of crux of convex optimization is that all locally optimal points are also globally optimal. And the proof here is on one slide. It's a very nice short proof. So let's assume not. Assume contradiction. Let's suppose that there is a suppose x is locally optimal. In other words, it's the region around it. In the region around it, it's the best point. But there is some point kind of further away, such that that point actually is better. Kind of goes like this. We have some point x here. And then in its region, this is the region R around it, it's the best point. So there's some point very far away here, y, it's better than x. So we're going to show why this can't be the case. And the idea is what we're going to do is we're going to construct a new point. We're going to think about the line between x and y. And we're going to build this point that lies right here, called z. And the way you actually construct that is z is this function. Z is theta times x plus 1 minus theta times y, where theta is this thing. So it's mostly x, but a little y. And let's think about this point now. So the first thing is that z, we know that z is feasible, right? Because x and y are both in a feasible set. So we're assuming constraint optimization here. X and y are both in a feasible set. So that also implies, remember, z is exactly that form of a convex set here. So that implies that z is also a feasible set. Secondly, let's try to make this 3. So the second thing is that we also know that f of z is actually less than f of x. We don't know it's actually inside R yet, but we'll get that. We know this. The reason we know this is that by convexity, you have that f of z is equal to that thing. This is what z is. Which is less than or equal to this thing by convexity. And then because we know that y is less than x, strictly less than x, we know that this whole thing is less than f of x. Theta is between 0 and 1. So we know that actually z also is a better point than x. And finally, this is just sort of with a little bit of arithmetic. The last thing we can show, last thing we can show, we can also show that x minus z are equal to r over 2. And the way is you just actually put this in here, those two terms here, you get this term here, you bring out the constant term, and that all reduces to just r over 2. And so we know actually that z is in fact within the radius r of x. So therefore, the whole thing is a contradiction, so we could not have had some point y that was actually better than f of x. This is a really, really powerful thing, right? Because what it means is that in order to find a global optimum of these problems, we don't need to consider the entire space we're talking about here, right? That's this crux of why this is working polynomial time. We don't need to worry about the space of all possible feasible points with the worry that there's some point far away that might be better than us, right? All we have to do is look in our immediate neighborhood, really as small a neighborhood as we possibly want to have around our candidate optimal point. And if that point is the best one in that very small neighborhood, we know it's the best point globally for the entire problem. And this is why it's kind of in some sense, this notion of convexity is such a nice one in terms of finding these optimal solutions to these problems. Yeah.
Is that Q2 is that final less than
this one here? So it's strictly less than, because we know that y is strictly less than x. That's the definition of a global optimum. I mean, there can be multiple optima. There could be a point where we have the same value as x, that's fine. But we know that f of y is strictly less than f of x. So because this thing is equal to this combination here, and theta is between 0 and 1, this is strictly less than f of x. Okay. F of y is less than it, and f of x is equal to f of x. So this combination here actually no, the defined theta here should be in terms of that r, which is greater than 0. Yeah. Okay. Yeah.
How do you decide on your theta?
In order to make this r over 2. What was your name?
On the ADI.
ADI. Okay. Yeah. Yeah. It's to make the math graph this r over 2, so we know it's within that radius.
Make R over 2.
And you can do whatever you want, but r over 2 is nice. It's less than r. Alright, so the time we have left, I want to talk now about solving these problems. So I set this thing up. It's great. Okay, so we have these problems. We have these convex problems where we know that we find a solution locally, it's the best one, or it's an optimal solution, right? It's as good as anything else. But I haven't actually told us, anything yet about how we solve the actual problem. So how do we actually solve the problem? And in fact, this is actually a really hard question in some sense. For certain problems, it can be very difficult. And so today I'm only going to give sort of this simplest approach to this, but it's one that actually does still underlie a lot of other approaches, so it's worth being very, very familiar with. This is something called gradient descent. So before I define gradient descent, I will have to define something called the gradient of a function. So, I should see my definitions still, but okay, so for f of for f R, the gradient of f, which is kind of a generalization of the derivative of f to vector input function, is the following. I write it like this: up down triangle of x. This is a vector of all partial derivatives with respect to the output function, with respect to every input to the function. This is a vector, and importantly, it's a vector in Rn. The vector is the same size as inputs to the function, and the components of this vector are the different partial derivatives with respect to the different coordinates of x. So the first one is the partial derivative of f of x with respect to x1, then partial x with respect to x2, etc., up to with respect to x. And the way to think about this is the point that kind of points uphill the most in that function. Right? So the gradient of a function, right, the derivative of a function, right, points in the direction, sort of the slope of the function, and it points in the direction that the function is increasing, and it kind of gives the slope of that function. This is in one direction. Well, in 2 dimensions, and higher, you get the same thing, where the gradient now is kind of a vector that points kind of in the steepest possible direction uphill from that function at that point. Right, this is very useful. It's another reason why continuous problems can be easier in a lot of ways than discrete ones. It's because now you actually have this information. You have this information about not just what the value of my function is, but what's the direction in which my function is increasing. And so, if you want to minimize your function, then the other thing to do is to take steps in the direction of the negative gradient. Right? So I'm going to take my point x, and I'm going to take a small step in the direction away from the gradient, right? The opposite direction. And that, in fact, is exactly the gradient descent algorithm. Yeah?
I just have a problem with the question.
No problem.
So, isn't it possible that the gradient of f with respect to x might also be a function of x?
Yes, well, it absolutely will be. So
it's not
yes.
n, it's like n to...
So when I write this, what I really mean is this just like, yes, it's a good point. Just like a of x is a vector, right? This is a vector, but of course it depends on x. Is a vector defined in terms of x. Now, there's other notation you might see, like people also write things like this, like the gradient of f evaluated, at x equals x0 or stuff like that. So you see those kind of things. The way I usually name this, the way I'll write this usually, is this term is the point I'm evaluating it at, and this term here is the point I'm taking the gradient with respect to. Now, oftentimes I use the same character there, so it can be a little bit confusing there, but I don't think it's actually that abstract here. In general, this will be a function, so that's actually a great question. This will be absolutely a function of x. So I have a function like, if my function, for example, I'll just write this one, is 2 norms squared. It turns out that the gradient of x and f of x is equal to x. So it's a function of x, of course, but it is, that, I write it just kind of like that.
So just to follow up, the x in the subscript is not binding to the x in the
Yeah, that would be a way of doing it. Yeah, that's more notational about what I'm predicting with respect to, and the second x is the one I'm actually evaluating it at. Just the reality is they're often the same, so I write it like this. It's less, it's confusing at first, but you get used to it pretty fast, and then it's not that confusing. Okay, so the gradient descent algorithm is actually very simple now. All we're going to do is we're going to have some function f. We have an initial point x0 and what's called a step size, which is some positive real value number that's bigger than 0. It has to be strictly positive. We're going to initialize the algorithm by just setting x to equal to x0. And then we're going to repeat by just taking x and subtracting a little bit of gradient off of that. So I'm basically just taking this function here, taking a little step in the opposite direction, the negative gradient direction, going there, and then repeating that process. And I'm saying repeat until convergence, but I'm just going to ignore that for now. I guess actually kind of scary when we're talking about how fast these things converge and what means convergence for passive functions. To say repeat until things stop changing or until you have 0 gradient. That will be good enough for our purposes. Alright, so why does this work? It's sort of intuitive why it works, right? It's sort of taking steps kind of in the downhill direction. And what's very cool about this is, of course, that you can get the downhill direction without having to evaluate all possible points around. You can just sort of look at your gradient, and that's the general, or negative gradient, that's the general direction. We're going to be a little bit more formal. I do want to say kind of a little bit more formally why this actually works. And so the theorem here is that if I take a small step in the negative gradient direction, so for some alpha, it's small enough, I actually will have a strict decrease of my function unless I'm already at a local minimum. So unless I'm already at a local minimum, if I do this, I will, in fact, decrease my function. This in some sense applies to the work. Not quite. It's also shown that it doesn't take forever and infinite sum of these things. But this kind of gives a nice indication that it's probably a good direction to take step. It requires two things here. First of all, we do require these derivatives exist. That f is differentiable. We'll see next time it's not always the case. There are very important problems that don't always have differentiability. But we'll assume for now that it does. And secondly, we also assume that, we don't assume anything about convexity of that. That can be either convex or non-convex. But we do assume that we're not already at a local minimum. In other words, the gradient is not 0. When the gradient is 0, that means that the function is kind of flat. And that does mean it could be a local maximum too, but we'll assume that we're not actually a question for that. We'll assume that the gradient is not equal to 0 at x. And so the way this works is actually very simple. In fact, it's just too formal given a very simple equation. But the basic idea is the function can be characterized. The way we can characterize this function is by what's called a Taylor expansion. And so what Taylor expansion does is it actually writes what that function is equal to as a function of so f of x plus some initial term b is actually equal to f of x plus the gradient of x times b, plus some terms that look like O of b, big O of b, the norm of b squared. And what that means here in this case is that there are 3 terms related to b squared, b cubed, b to the 4th, etc. But they're all these sort of small norms. They're going to be smaller than the norm of b squared. And the way to kind of think of this visually is that if you have a point x, its first order Taylor expansion is actually a linear approximation to the function at that point. And then the rest of the function kind of is only smaller terms than that first approximation. So now, having this, if you'll sort of grant this, And by the way, this is now, we didn't really define why this is the case, but this is kind of the mathematics of higher order, higher dimensional matrix calculus properties here. Now everything follows pretty easily. So now if I look at what this term means, this term here, my negative greater than my v term, so I just plug that in and I'll have to put the Taylor expansion. So what I have is that f(x) minus v, right? Which is where v is that thing. I'll actually even call it, I'll call it like alpha. V is actually just the gradient. This is equal to f of x plus v, I guess negative or x times alpha plus some term that looks like this. We can have higher powers here too, but assuming this is small enough, I actually can take this whole thing and replace it with, we know it's less than, so constant times this guy. Because small enough so that the terms of higher order. And then now we just have to sort of throw that's sort of actually kind of the subtle step there, is if you can actually bound that, knowing that this term is small enough. But after that, it's all pretty straightforward. So now we just sort of take terms together. So this equals f of x minus this in fact is the same thing here. So we have just alpha minus squared c times the norm here. Which we know is less than or equal to f of x, as long as we take alpha to be small enough. As long as alpha is less than whatever c, and as long as this term here is positive, we know that we can decrease their percent. And this, by the way, holds entirely independent of whether the function is convex or not. It's a general property, right? Questions on that? Yeah.
How do you say that
Oh, this term has to be positive here. We're subtracting something off, so otherwise it could be.
the C comes from basically the order of.
Yeah, C is just basically some bounding thing where if a student is small enough to bound it. Yeah, so the order of how you shoot this, it doesn't really matter. You can do that, right? You can first say for any function small enough, C is at most this thing, and so I'm just going to make alpha even smaller. So as alpha gets smaller and smaller, you can do that. Yeah, there's a little bit of subtlety there, so I don't know why I could have said that. But that all kind of works.
So you choose alpha, which is smaller than 1 over C.
Yes.
How do you compute the C?
You don't worry about that. I mean, in practice, yeah. You don't worry about making it exact here. Because that's just a bound anyway, so it's just showing there's some small alpha for which this doesn't bound.
Is it a better idea to put a small O in the Taylor's function? Just because it makes much more clear.
Yeah, you could put a small O, I guess. That would be a little bit more. I mean, there is a d squared term. It's just that there's other terms that are all smaller than this. Alright, so maybe actually while I plug in my battery here, I'll ask the next question. It's a different version here. We're almost done here. I only have one slide or 2 slides after this, so kind of fast, but I want to propose a different algorithm for everyone here. This is not looks just like gradient descent, so it works the same way. except that we are picking the gradient in step. We're not picking the gradient in step in the direction of. We're instead picking some other direction, v. The only criterion on v is that it makes a negative inner product with the gradient. So the v, take the inner product of the gradient and v. That's always less than 0 by some amount. And so, would that certainly less than 0, right? And so the question is, does that converge? Converge always, only for convex cases, only for non-convex cases, or never. I don't know about that. I want to get through a couple next slides here, so I'm going to go on this one. Alright, so we're going to go the next 10, 20 seconds.
A little bit off.
Alright, I'm gonna close it now. So everyone's okay. Maybe okay, so it actually is tricky because depending on sort of how much you overthink it, actually, you can come up with different answers here. In general, the answer is yes, so it does actually converge for both convex and non-convex functions. And the reason is that if you have this thing, and again, this sort of, whether or not you get this will depend on sort of what you think, what you want to let depend on what other quantities here. But basically, if you have this, if you know this thing is negative, you can replace this whole thing here, with just alpha epsilon for some small epsilon. And then you still have the alpha d squared here, but you can still make alpha small enough such that the alpha c norm of v alpha squared is less than alpha epsilon. Right? So because this term here has an alpha squared, this term here has an alpha, you can always pick alpha low enough. You want to pick alpha last. You can always pick alpha low enough such that in fact the v makes one. So this attribute criterion is sufficient for both the convex and non-convex cases to get a decrease. Alright, while you're thinking about that, let me say a few last things. So the last thing I'll say is that picking alpha is not just a matter of sort of theory, though it's a total pain in theory, but it's also kind of a pain in practice. When you are running gradient descent, you have to actually pick alpha and for some value, and depending on what alpha value you pick, you may get very slow convergence if you're taking steps are too small. You may get good convergence, or you may get convergence that actually tend to diverge, or just something converge very fast because it's bouncing around so much. You take a step that's too big, it sort of overshoots, you go back, that's something kind of like that. I'll leave it till next time to mention these last two things. I will mention the very next slide next time. But the only thing I'll say to end up here is that for the constraint case, in some cases, you can adapt gradient descent to work on that by essentially you can easily write a projection onto your set. Then this does work. But otherwise, sometimes writing that projection, like finding a close point, nearby point in your set, can be as hard as solving the original problem, so you're kind of lost. And then the last thing I'll say is, if f is not differentiable, but still continuous, it may not have a gradient at all. But it does have something called a subgradient, which is kind of just as good for our purposes. It lets you run something very similar called substrate descent analysis, gradient descent, and so you can do everything as we were doing before. It still typically works pretty well in practice, though in theory there are much more hairy issues. Alright, so we'll finish up this next time and talk about the